Okay, most of you seem to be jumping right to a bunch of calculations, okay? And some of you are not starting off just right here. But if you jump to the calculations and get them right, of course, you're going to get the right answer, and many of you are trying to do that. And I really would rather see you write this out in a way that reinforces what's going on. Otherwise, you forget what's going on, you get into a test, you get confused, and all of a sudden you don't remember what to do, okay? And also, you just simply don't remember it long term, so that when you need it next year, it's not going to be there, okay? It's also a principle that applies to a lot of other things. So if you have this function, let's say it's 5x minus 8 times 6x squared plus 9x plus 3 equals 0. Okay, well, you want to write out the equation. Not everybody's even writing out the equation. You just start with the thing and do your calculations, and you're probably doing the right calculation. You're not expressing it in a way that's going to help you as much in the future. Follow the steps. Don't skip steps. One step, and you write this thing is equal to 0. Then you notice you have two factors equal to 0. The other way it's going to be 0 is if this factor is 0, or this factor is equal to 0. Now at this point, have at it, okay? I mean, write out the details, but do it in a coherent fashion that presents it coherently. So if you're being graded, your grader is going to be able to see what you're doing and understand the flow of your thoughts, so that even if you make a mistake, you're likely to get more partial credit. I mean, just for the practical purpose of doing well on a test, it's very helpful if you present it as coherently as possible. It also teaches you to present your ideas coherently, which spreads out into other courses that aren't mathematics courses, okay? It helps you learn what it takes to present things clearly. And it reinforces the mathematics, as I keep saying, in a way that is going to be very beneficial to you, okay? Okay, some people do need to see me work this. Okay, we've broken this into two equations. Every one of these breaks into two equations. Okay, so you got 5x minus 8 equals 0. Add 8 to both sides. The 8's going to go away over here. You're going to get this. Divide both sides by 5. And you're going to get x equals 8/5, which is 1.6. This equation is going to get x equals -9. That's the minus square root of 9 squared minus 4 times 6 times 3. And you're going to divide that. Yeah. Okay, that's all right. You divide that by 2 times 6. And in this case, you're going to get something like this: -9 plus or minus square root of. So 4 times 6 times 3 is 72. 9 squared is 81. Just coincidentally, you end up with square root of 9 here. I didn't intend that. And you're probably not going to end up with anything nearly as sweet as what I've got here. Okay? I just lucked out. You might luck out too, depending on your values of A, B, and C. So I end up with -3 and -6. Now, just to illustrate, well, you probably do, in fact, end up with a negative under your radical. Okay, so if the equation was just change the 3 to a 4, then we end up with x and I'm not going to write out the details. They're just like this, except I'd have a 4 here. And instead of 72, I'd have 96. So I'd have square root of -15 over, well, let's just say over 12. Okay. And the square root of -15 is not a real number. But you break 15 into -1 times 15. So that's going to be the square root of 15 times the square root of -1. Square root of -1 is I, imaginary number. And you don't need to take your calculator and calculate that. You just leave that as the square root of 15. It's fine. And if you need to calculate it, that's okay. But generally, at least often it's not necessary. So there are your two complex solutions. Okay, I'm gonna have to go ahead and cut to the solutions. So your g of x function equals 0. So we got 6 and we got 8x squared plus 11x minus 6. Okay, so for a equal to 6, b equal to 8, and c equal to 11, we would get this. So we want to write this out. As I said, you got x squared plus 6 equals 0. Really want to write that, or 8x squared plus 11x minus 6 equals 0. Okay, how do we solve this? Well, you know, this is actually a quadratic function, so you could use a quadratic formula. Your coefficient of x squared is 1. Your coefficient of x is 0, so b would be 0, and your c would be 6. However, you don't have to do that. You just subtract 6 from both sides. So x squared equals -6. Well, x squared equals -6. X equals plus or minus the square root of -6. Okay. And that equals plus or minus the square root of 6i. So that was actually pretty straightforward. Okay, over here. X will be negative 11 plus or minus the square root of 11 squared minus 4 times 8 times negative 6 over 2 times 8. That comes out negative 11 plus or minus the square root of, so that's 121. And that is 32 times 6, which is 192. That's over 16. And the square root of 192 is about between 13.8 and 13.9. And that would equal, again, approximately, that would be like almost negative 24 over 16. Which would be negative 1.5. Or it would be kind of like 3 over 16, which is like 0.1875, but that's like only 13.9, but still might be 0.19. Okay, it'll either round off to 0.18 or 0.19 if my mental calculation is correct, but use your calculator, you're going to get it more accurately. Okay, that's perfectly valid. Okay, and this last one, I'm not going to do it. It's the same thing. Okay, this one will have 2 zeros, real zeros. This one is probably also going to have 2 real zeros, but maybe not if your A is big enough. Okay. But I'm pretty sure your G is going to be big enough that its square is going to be bigger than 4 is. And I mean, so that's how you do it. Let me just reinforce once more. You want to write out the 2 equations or more equations. You could have more factors. Okay. And then solve each one separately. And every solution gives you a real or a complex zero. Irrational function. Now this is probably the most algebraically demanding part of the course. Now, if you're in the MDE 61, which some of you are, you have a good idea what I mean. But you know, if you're not, you're about to find out. If you don't already know. Okay. So you got to be careful with your algebra and make sure your algebra is up to the task. It has a form of a polynomial divided by a polynomial. Now I'm just going to cut to the chase and look at a rational function. Example. And we're going to analyze this one. R of X equals X plus 5 over X minus 3. Now let's discuss this for a minute. Let's give me a couple of answers. Okay, well, people might give me a real quick answer to this. So what I asked for is, how can you give me a fraction that's equal to 0? Okay, that means the numerator and the denominator would make a fraction 0. So let's just kind of put a little room up here, make sure I got this on the camera. This would be nice if we knew this one. Yeah, okay, okay. Well, I think 0 over 723 is 0. Everybody agree? Okay. Well, can you write down another fraction that would equal 0? Everybody just write me down another fraction. It's not just 723. Okay. Another fraction that equals 0. If you can't restrain yourself, you write it. Yeah, okay, not looking at everybody, but people are doing that, and what you wrote down is correct for the R of X function. Okay, so, you know, I'm saying 0 over 2 equals 0. You know, I didn't say my favorite, which is 0 over 7,589 equals 0. I was hoping somebody would get that one, but it's okay. Now, just kidding, in case you didn't notice. Okay, so now how could this be 0? Well, it's 0. In order for a fraction to be 0, the numerator has to be 0. And of course, the denominator can't be 0 because division by 0 is undefined, right? So the numerator is 0 if X equals -5. Now that should be pretty obvious if you understand that the numerator has to be 0 in order to make the fraction 0. It's obvious then that -5 makes X plus 5 equals 0, right? Now, if your numerator is 4x squared minus 12x plus 17, then you're going to have to do a little work to figure it out, and you're going to have to write it out just like we did over here. You're going to have to say the numerator is 0 if whatever your numerator is, set that equal to 0, and then figure that out. Okay, just like you've done for these problems. Okay, well, already we have a hint about the graph of this function, don't we? And so the graph of this function has to go through the point 5, 0. So we've got a point on the graph. Now we're not going to graph these functions by substituting a bunch of points. That's, I hate to say it, pointless. Okay. We're going to graph it by looking at its characteristics, just like we don't graph polynomials by plugging in a bunch of points, right? We graph polynomials by figuring out where their zeros are and what the long-term behavior is, long-run behavior, whether as X goes infinity, negative infinity, and also the Y-intercept, okay? Now, can you give me the Y-intercept? one principle that ought to be firmly established from the work we've done on polynomials is that the y-intercept is on the y-axis, and on the y-axis, x equals 0. So the y-intercept occurs when x equals 0. If you've done the homework, you've done that on a dozen or more problems. So ask yourself, if you weren't able to answer this question immediately, how do you miss that principle when you're working the problems? Okay? And how can you approach the problems so you don't miss important principles? Okay? I've also said it a lot of times in class, but I expect that to go over your head. So you pay attention to all sorts of things, but trying to reinforce what you're getting. So let's make a note here. So you just can't forget this. You just can't not know this in your depths of your mind, okay? The y-intercept is the x equals 0 point with 4 exclamation points. Make yourself a note. Never to not know that. Okay. So anyhow, okay. So if x equals 0, what's the value of y? Well, so y equals r of 0. In other words, you plug 0 in here, which is 0 plus 5 over 0 minus 3, negative 5/3. So that's like, negative 1 2/3 between negative 1 and negative 2. So I'm going to say, okay, here. And now I've got some kind of a hint about this graph. Like it's got to get from here to here somehow. And it can't go through the x-axis because the only way r of x can be 0 is for the numerator to be 0. And the only way the numerator is 0 is if x is negative 5. And I said negative 5 and I put 5 0 up there, didn't I? And that's a very good example. That was confusing you. A good reason for it. It should have been negative 5 0. Now, if x is a big negative number, what can you say about r of x? Well, think about it. If x is like negative 1,000, a number bigger than either 5 or 3, okay? Negative 1,000. Then what do you have here? You have negative 1,005 divided by negative 997, right? Now, if 1,005 is this big, show me with your hands. Show me how big 1,005 is. Okay. I want to see hands. I want to see them separated. Okay. I want to see everybody with hands. Okay, good. Thank you. That really wasn't all that hard, was it? Okay. Now you can't. That is, I put your hands down. Put your hands back up there. Okay. Now there are your hands. This is 1,005, right? How big is 997? Pretty much the same, isn't it? Okay. Yeah, you can't even move your hands that little bit unless you're nervous. Okay. And nobody seems to be all that nervous. Even math class, that's good that you're not that nervous. Okay, that makes sense? Negative 1,005 and negative 997, or actually it should be negative 995 negative 1,003, shouldn't it? Okay, but they're practically the same size, right? So when you divide them, what number is the result going to be close to? Fill up your number of fingers. Yeah, if you divide a number by a number that's close to it, you get something pretty close to 1, right? And thank everybody for using the correct finger. Okay, now, okay. You need to understand this, otherwise you're just blindly following the rules. So, as x goes to negative infinity, the numerator and denominator are nearly equal, aren't they? And both negative so R of x is close to 1. Make sure you understand that. Okay, well, if this is negative 5/3, well, that's between 1 and 2 and a little closer to negative 2. So it's like negative 1 is about here, negative 2 is about here. So that means positive 1 would be about here. So here's your line where x equals 1. Sorry, y equals 1. All right, so that's okay. It's a line where y equals 1. And the value of the function is going to get close to 1. That means that if you're over here, the function has a value close to 1. And then it stays kind of close to 1, but then it starts curving down here. And maybe it goes down like this, you're not sure, but it comes back to here. And I've got a big problem with that. Because how are we going to get back up close to y equals 1? Because when x is a big positive number, again, this is two positive numbers that are practically the same, right? So now I've got myself a conundrum here. I've done some boneheaded thing. My problem is I don't have another value of x that makes y equal to 0, do I? Okay. So there must be something that I'm not thinking of. Well, here's what it is. And you'll get into similar confusion if you don't do everything. So the one thing that I didn't do that you always want to do is you want to figure out where the denominators are as well. Okay? So and this is what's going to rescue us out of the conundrum. Denominator is 0. When x equals 3. Okay. R of x is undefined if the denominator is 0. So the graph can't cross the line x equals 3. If it did, that would give it a value at x equals 3. Okay? So that's going to resolve our dilemma here, and we'll see how. So let's see, x equals 3 is about here. R of x is undefined on this line. The other thing is that when x gets close to 3, x minus 3 gets really small, right? Okay. Now, if x is close to 3, how big is the numerator? Close to what? Show me with your fingers. If x is close to 3, what's x plus 5 close to? X is close to 3. Well, if x was 3, what would x plus 5 be? 3 plus 5 is, show me with your fingers, 8. Okay. What should be oriented here? Okay. It's kind of important to understand these things rather than to just do things blindly following a bunch of rules. If you understand it and you know the rules, then you know it deeply and you're not likely to forget it, and you're going to have a principle rather than a plain rule. Okay. Rather than uninformed rule. And the principles aren't that hard to understand. So if x is 3, the numerator is 8, right? Now, if x is close to 3, what's the numerator close to? It's close to 8. Okay? If you're close enough to 3, you get as close as you want to 8. That's an important idea. That statement is very important. And the idea of limits when you get the calculus. Okay. Okay, so let's just accept that x is really close to 3. Now, how big is 8? Want to see hands? Come on, you can't waste time. Y'all are capable of this. Good. Okay, there's 8. Okay. Now, if x is really close to 3, how big is x? How big is x minus 3? Really small if x is really close, isn't it? But give me a number really close to 3, 3.002. How close is that? 0.002. That's 1/500th. Okay? You can't even show me that with your hands. If this is 8, 0.002 is too small to indicate, right? Okay. So if this is 8, then x minus 3 is going to be really small, which means if x minus 3 is this big, how many times does that go into 8? Say, a whole lot of times. Yeah, pretty many times. Well, not many times, just to get it. Okay, it goes in a whole lot of times, doesn't it? A whole lot of these to make this. And as these get smaller and smaller, it takes a whole lot of them. Okay, a lot more. Okay. So when you divide x plus 5 by x minus 3, if x is close to 3, you get a big number. Now, if x is a little more than 3, this is going to be a positive number, and you're going to get a positive. If x is a little less than 3, like 2.9, it's an easy number, then you're going to get a negative number. 2.9 minus 3, negative 0.1, right? So if x is less than 3, you get a small negative number. If x is greater than 3, you could get a small positive number. Meaning that on the right of this thing, the graph is going to go up rapidly as you approach x equals 3. Because this stays positive as long as x is on this side of the line. X is bigger than 3. This number gets tinier and tinier. It goes into x plus 5, which is close to 8, more and more times, right? And there's no limit to how many. There's no limit to how small x minus 3 can get. So there's no limit to how big x plus 5 over x minus 3 can get. On the left, it's the same thing, except you're dividing by a negative number. So as you get close to x equals 3 down here, your graph has to go way down like this. You have a vertical asymptote. That's what a vertical asymptote is. If you understand that, then you're well on your way to understanding rational functions in a way that does more than just follow a few rules that you're going to forget as soon as the test is over. Okay, so my original graph probably doesn't look like this. Okay, it doesn't really go down here and turn around so it can get up to here, because it can't get up to here except by going through 0 or by changing sign when you go on the other side of the line. And that's what actually happens. So here we go. So let's try to draw a better graph. So we're going through -5, 0, which was here. So we got to go through here. We've got to start close to y equals 1. So we're just going to go through here, and then we're going to come down like this. That represents everything that we've talked about on the left-hand side. And on the right-hand side, well, it's easy to verify that x goes to plus infinity. This is also going to go to 1 because these are still going to be the same size and the same sign, right? So you're going to come close to the line y equals 1, but you're going to come down from this line. So it's just going to do this, right? It's kind of boring. Okay. Okay. What basic function does that look like? Okay, so I think a lot of you saw it. It took me a lot of time, but it's like the basic reciprocal function, except that occurs on the y-axis here with the x-axis here. And the x-axis would actually be like the line y equals 1, okay? So it's a lot like the basic reciprocal function, which has a graph that does this and this. And basic reciprocal square does this, right? Basic exponential function does this, squaring function's a parabola, cubic function does this. You got to know those things. And you got to know those things in order to graph rational functions with any kind of meaning. So what it comes down to, and I won't go into detail on this is just a vertically stretched 1 over x function close to this line. It's like a vertically stretched 1 over x function. It's been moved over 1 unit or over 3 units. This is line x equals 3 and up 1 unit. Okay. It's just a translated and stretched 1 over x function. And there it is. And it's actually, it's really the 8 over x function. The numerator is 8 and the denominator goes to 0. Okay. So there's your vertical stretch. You don't have to know that. It'd be good if you do, so if you understand that, think about it a little bit. But it's not necessary. I'm not going to ask you to do that, except maybe on an extra credit problem. Okay. Okay. So that's a whole lot. That's really the process you go through to graph any rational function. Now I'm going to give you another one that's really not Any more complicated. The questions you ask are easy to answer, but you're not familiar with it. So let's think how well you can do. Okay, now let's say we have this function. I'll give you some questions. Get used to asking yourself these questions. What's the first question we answered? Where's the numerator? 0. And then where's the denominator? 0, right? First and second question. See if you can write out the answers to these questions. Give you a couple of minutes. Shouldn't take long. Okay, third question that somebody is answering, and some of you are answering instead of answering one of these questions, but it's equally important. What's the Y-intercept? Okay. So let's answer all three questions. Okay. Now, numerator 0, what's that mean? Well, what's the numerator? It's x minus 5. Set that equal to 0 and solve it. Well, you don't even have to write out a bunch of equations, but just to show the form. Sometimes your numerator gives you equations that you have to do a little work on, right? Have a good weekend. So that's x equals 5. Or x equals -3. Now, let's stop here for a second. How does that information go in your graph? Okay, here's a graph. Show me what this information, or represent this information somehow on your graph. Okay, a lot of people got this pretty quick. Just be sure. The numerator is 0 when x equals 5 or x equals -3. So the graph points include 5, 0, and -3, 0. And that's because, of course, if the numerator is 0, the whole thing is 0. So we got 5, 0. -3, 0. Okay, denominator 0. Now, for sake of time, I'll write this up, and I'm sure everybody got the numerator. You got this. I'm just writing it out, and please write this out. Doesn't take long. It took me, what, 10 seconds to write that? Not going to delay the rest of my life very much. Okay? So we get x equals -2. Or x equals 6. So vertical intercepts, or vertical asymptotes, sorry. At x equals -2 and x equals 6. Now, I had this pushed over, so I'm not sure everybody saw where these points were. I think it's pretty obvious. But again, points 5, 0, -3, 0 go here and here. Those are points on the graph. Okay. You got vertical asymptotes. These aren't points on the graph. They're points where your denominator goes to 0 and your numerator doesn't. Okay. And then we have to say, okay, well then, x equals 6. I really do that. I do. Is a vertical asymptote, and x equals -2 is a vertical asymptote. -2 should move over just a little bit. That's okay. Also, the y-intercept I've written that kind of small, but I've just written it out with zeros where the x's are. And that's going to give us -5 times 3, which is -15, and 2 times -6, which is -12, which reduces to 5/4, or 1.25. Okay, so here's the y-intercept. But these steps are always the same. The only thing that differs is the expressions you have in the numerator and the expressions you have in the denominator. You got to set each one, the numerator equal to 0, set the denominator equal to 0. And then you know what to do. Okay. So now we have this information on the graph. Now we got to look what happens as x goes to infinity. Well, again, if x is really big, if x is 1,000, all these numbers are near 1,000, so you still have x close to 1, right? Or y close to 1. So the same reasons as before. Y equals 1 is horizontal asymptote. So now we're ready to draw the graph. It takes a little practice, but we have to start over here close to the horizontal asymptote. The only place we can go through the x-axis is here. And the only place to the left of the asymptote we go through the x-axis is here. And it's going to do this. Okay. On the other side, well, it's got to come down from here. It's an asymptote. It's got to be up here for a number of reasons. You can reason it out. If x is bigger than -3, it's close to -3. This is negative. This is positive. This is positive. This is negative. You got a negative over negative. And it's big because be close to x equals, I said x equals 3, x equals 2. Yeah, okay, so it's going to come out like this. Now it's got to come down and go through this point and this point, then it's got to approach this asymptote. So about one way that can happen is it does something like this. I kind of missed that point, but you get the idea. Then over here, it doesn't go through the x-axis. We've already taken account of both of our zeros. So it's going to do this. Got to approach these two asymptotes. All right. Now your open math is going to run you through the same reasoning process. You always ask the same question. The answer isn't always the same. For example, yes, it's clear it has zeros at -5, 3, and -6, right? So we can quickly kind of skip all the details and just say, okay, -6, -5, and at 3, we have zeros, and we have a vertical asymptote at x equals -1. Now you might have to go through that a little more slowly, but there it is. Okay, now we got 3 places we got to go through the axes. As x goes to infinity, y goes to infinity this time, because if x is a really big number, you got 3 really big numbers up here and just 1 really big number down here. Okay, so this big number over this big number gives you something close to 1. We're still left with 2 other big numbers that you multiply, so they go up really fast. So it's got to go up really fast this way. And as x goes to -infinity, well, y still goes to infinity because you get 4 really big negative numbers, right? 3 in the numerator, 1 in the denominator. 4 negative numbers multiplied, divided in any order is going to give you a positive number. Same reasoning goes here, though, that any one of these big positive numbers would be divided by this and leaving the other 2. So it would go up like this. Okay. So x goes to -infinity, y goes to +infinity. So what happens is you come down through here, you turn back around, and you go up to this asymptote. Then you come up and down here, you go through this point, and then you go on up. Okay, well, I did that kind of quickly. I just wanted to demonstrate that you don't always have a horizontal asymptote for these functions, okay? A lot of times you do, but in this case, you certainly don't.